Okay, hey everybody. This is the supplement on section 15.5, surface area. As I kind of mentioned before, maybe surface area isn't the most important topic in chapter 15, but I think we will see some usefulness of it in chapter 16. I think it is good to take a little bit of time and cover this material in preparation for the next chapter. Okay, so let's start with the basic idea of surface area. And we're going to recall from Calc 2 the idea of arc length. And we're just going to quickly go through a derivation of the arc length formula for a single variable function. So here I have a function y equals f of x going from a to b. And if I'm interested in finding the arc length, I'm interested in finding the distance between AF of A and BF of B along the path of the curve. And remember, the way that we approached this was to take a little chunk of the curve. And if we zoom in on a small chunk, say of width delta x, where delta x is small, we have a bit of curve there. We see that from the left to the right sides of this window, we have a vertical deviation, delta y, and a horizontal deviation, delta x. And then we note that the straight line connecting the left endpoint of the curve and the right endpoint of the curve in this window, if I pick the small window and if my function is nice and continuous and all of these good things, then the straight line connecting those 2 points for a small window should be pretty close to the function to the curve connecting those 2 points. So the red line distance should be pretty close to the distance of the black curve in this small window. And of course, this red line distance is, maybe we'll call it delta L for little change in length. And it's going to be square root of delta y squared plus delta x squared. Or we can rewrite that as square root of delta y over delta x all squared plus 1 times delta x, just factoring out that delta x from under the radical. And then this leads us to, we would sum up these little approximations to get an approximation to the arc length of the whole curve, and then we would take a limit, and we would get that our arc length, maybe we could call it S, is the integral from a to b of square root of 1 plus f prime of x squared dx. So this was what we got for arc length. We note that it would be a bad approximation to just kind of look at a single window from A to B and draw a straight line between the two. That's not really capturing what's going on here. So the important idea is taking a small window and then, in some sense, we're kind of using a linear approximation here. That's not exactly what it looks like, right here, because we don't really see the tangency so directly. But note that this is actually a secant line. This red line is a secant line, so it is kind of like an approximation to the tangent line. So we're using the idea of a small window and then summing over a bunch of small windows, and the idea of the tangent line or the secant line being a good approximation to the function under some conditions, of course. Okay, so if we want to talk about surface area, we are bumping up one dimension. And suppose we have a surface. Maybe it'll be like a paraboloid in the first octant. we have some surface that we are interested in, and we want to find its surface area. I'm going to consider a point on this surface. I'm trying to draw it somewhat nicely here. Say this is a point of interest. I'm going to take this as a point that is within some little chunk of this surface. And this chunk is going to be above a rectangular region in the XY plane. Like that. So if I think about this little chunk of surface, it's going to be somewhat nonlinear. But perhaps I can approximate it with just a plane, with just a little chunk of a plane, which will be linear in both directions. Now, I don't know how to find the area of this complicated, curvy, even small section of surface, but I do know how to find the area of a plane. If I take an anchor point, so to speak, and I have, say, a vector B and a vector A that lay out the two sides of that little chunk of a plane, then I know that this little chunk of area here, maybe I'll call it dA, or this will actually be, I suppose, dA, and the approximation to that will be the area of this, what turns out to be just a parallelogram. And that's going to be the length of A cross B. That was one of the properties of our cross product. So making use of that here. Okay, so if I cut my overall surface into a bunch of little chunks of surface, I can maybe approximate a curvy chunk of surface by a little flat surface. And the other key component is we know that derivatives do a good job of approximating. So we would like this little chunk of flat surface here to be maybe like the tangent plane at this point under consideration here. And if I'm going to make a tangent plane, it probably is easiest if I choose A and B to kind of be above a box that has sides parallel to the X and Y axes, so that I can use just my normal partial derivatives instead of some kind of goofy directional derivatives or whatever. So I'll consider A to be the direction that's kind of moving in the X-axis direction, and then B to be the Y-axis direction. So A then, well, if I move a little bit along the X-axis, a distance delta X, then its first component, its I hat component, is going to be delta X. It's not going to move at all in the Y direction. And then its height component, its K component, is going to be Fx delta X. And then similarly for B, when I move a little increment in the Y direction, well, the X component doesn't change at all. The Y component is just delta Y, and then the change in height moving in this direction is Fy delta Y K hat. Okay, so let me take the cross product of these two vectors. So A is delta x comma 0 comma fx delta x, and B is 0 delta y fy delta y. And this gives me I hat times, well, I get 0 times fy delta y, and then minus fx delta x delta y. Get that minus. For j, I would get, going top left to bottom right, I get fx delta x times 0, and then minus delta x fy delta y. And for k, going top left to bottom right, I get k times delta x delta y. And going the opposite direction gives me 0 times 0. Or this is just the vector minus fx minus fy1 times delta x delta y, or times delta a if you prefer to write it that way, a little chunk of area in the xy plane. Okay, and then lastly, what is the length of A cross B? Well, that's the square root of fx squared plus fy squared plus 1 delta A. And then, of course, we would kind of imagine adding up a bunch of these areas, getting an approximation to the surface area, and then taking the limit as delta x and delta y both go to 0, and we would come up with this definition. The area of a surface with equation z equals f of xy, where xy is in some domain and fx and fy are continuous, is given as the double integral of the square root of fx squared plus fy squared plus 1 dA. Okay, so let's work through some examples in surface area. We're going to start off with a couple of simpler examples. So example 0 here, a pretty simple example. Compute the surface area of the portion of this plane, z equals 2 minus x minus y, that lies in the first octant. Okay, so I see whenever x and y are 0, z is 2. When x and z are 0, y has to be 2. And when, oops, y is 2. And when y and z are 0, x has to be 2. So this is my plane. And I'm looking for this surface area. And I'm actually going to do this a couple of ways. I'm going to do it two different ways. One, we're going to start with just geometrically, just looking at this geometrically. So I noticed that this area that I want to find is actually a triangle. It's kind of, a tilted triangle in 3 dimensions, but it's just a triangle. So I can imagine that this triangle has a height and a base. So it has a base, it has a height, and I could find its area as 1/2 times the base times the height. I noticed that the base here, if I just look at the xy plane, well, I have a right triangle with 2 sides of length 2, so the hypotenuse then has to be square root of 2 squared plus 2 squared is 2 root 2. So I see my base is 2 root 2. And then what's my height? What's the distance from this point to this point? Or, well, that's the distance from what? Well, that the midpoint between 2, 0, 0 and 0, 2, 0 is 1, 1, 0. That's just this midpoint here. X and Y are both 1 to the point 0, 0, 2. And nicely enough, this is an easy distance to do. I get 1 squared plus 1 squared plus 2 squared. That's 6. And then square root of 6. The 2's go away. I get square root of 12 or 2 square root of 3. So in this case, my function was simple, a nice linear function, plane. And my region was simple. So I was able to use just basic geometry to get this answer. Let's see if we use the integral if we get the same answer. Hopefully we do. Okay, so z equals f of xy here. df dx is -1. Partial f with respect to y is -1. And of course, fx squared plus fy squared plus 1 equals 3. And that's under the square root. So for our surface area, the area of our surface, it's the double integral of square root of 3 dA, or this actually is just square root of 3 times the area of the region over which we're integrating, or it's just the area of this triangle. So it's square root of 3 times 1/2 times the base width of 2 times the height of 2. It is 2 root 3. Okay, so that was, certainly a pretty simple problem to work through. We will get to some more challenging problems. One little note on surface area. In Calc 2, you might have seen areas of surfaces of revolution, and even in Calc 2 and arc length, if you just picked kind of a random function and tried to, a random function, a random region, tried to find the surface area, chances are pretty darn good you're not going to be able to compute the integral, right? So typically, you're kind of stuck with one of two scenarios that if we're in a class and working through this, we want to understand the ideas. So we typically cherry pick problems that we can end up doing the integrals. And often that means maybe a problem ends up with a lot of symmetry that we can really leverage, or maybe it ends up to where this whole inside bit, the square root, all just turns out to be a constant or something like that. So sometimes that's the case. Or the other case, the kind of more practical case, is if you actually need to solve a problem like this, you would go to some kind of numerical method. But of course, understanding how to set up the region, what integral you're actually looking to solve, and so on is the important part. So that's really what we're trying to get out of this, is understanding how to set up the integrals, understanding how to set up the regions, how to work through some of these calculations. And it's less about doing a long integration problem. Okay, so let's look at example 1 now. Now, example 1 uses the same plane, but a slightly different region. So let me redraw the plane. So that's the plane that we're looking to find the surface area of, but now we're only looking for the surface area that's above this circular region here, this quarter circle region. So really, I'm looking for this surface area here. So at kind of the top point near 002, it looks basically like a triangle, but as it comes down, that bottom shape is kind of a rounded piece there. Okay, so I note that my region has changed. My domain D here is different. It's not this entire triangle that it was before, but it's now this little chunk of a circle. But note that my function itself hasn't changed. F of xy is still 2 minus x minus y, which means my integrand is still the same. And then, of course, this is just square root of 3 times the area of this little quarter circle of a circle of radius 2. Well, a circle of radius 2 has whole area of 4 pi, and then we're taking a quarter of that. Oops, dumb mistake there. Circle of radius 1, my plane intersects at 2, x equals 2, and at y equals 2 is where it intersects those axes. It's going to say something didn't quite feel right there. There we go. So that's root 3 pi over 4. So something interesting that I see is for this particular plane, z equals 2 minus x minus y, its surface area seems like it's always going to be just square root of 3 times the area of the domain of integration. That's somehow like fundamental to this plane. So whether I pick a bigger or a smaller domain of integration, whether it's a curvy domain or a nice domain with flat sides, I'm always going to get square root of 3 times the area of that domain. Because as long as this plane stays the same, this integrand stays the same. So in a sense, this plane, what it's doing is it's stretching the xy plane by something like a factor of square root of 3 in a certain direction. Okay, let's look at the next example then. Here we're also going to work with a plane. We won't be working with just planes this whole time, but for these first couple we are. So let's compute the surface area of the part of the plane x over a plus y over b plus z over c equals 1. Here a, b, and c are positive. We want the part of this plane in the first octant. So again, when y and z are 0, x over a is 1, which means x is a. And then similarly, y is b and z is c. And those are all positive numbers. I also see that z equals c times 1 minus x over a minus y over b. This is f of x and y. Partial f with respect to x is negative c over a. And with respect to y is negative c over b. And my square root that goes inside of my integral up here is going to be square root of c squared over a squared plus c squared over b squared plus 1. And we can simplify this a little bit. We can get a common denominator, b squared c squared plus a squared c squared plus a squared b squared all over a squared b squared. And so I'm integrating over this domain D in the xy plane. I'm integrating this square root, or that's 1 over AB times square root of b squared c squared plus a squared c squared plus a squared b squared dA. And again, we see that this whole integrand is just the constant in terms of x and y. So this is just 1 over AB times that square root times the area of the domain that I'm integrating over, but I see that that's a triangle with sides A and B, a right triangle with sides A and B. So I see when all of this shakes out, I just get 1/2 square root of b squared c squared plus a squared c squared plus a squared b squared. So kind of interesting little formula. Okay, so now let's look at some functions that aren't just planes. So for the next example, let's compute the surface area of the portion of the cone, x squared plus y squared equals z squared, that lies above the disk, x squared plus y squared less than or equal to 4. So I do note that when x is 0, I have y squared equals z squared, or z is just absolute value of y. And similarly for the case when y equals 0, I see this is just a cone like this, 45-degree lines. Looks like that. And above the disk, x squared plus y squared equals 4, less than or equal to 4. That's my region of integration. Okay, so I need to set up my integral, which means I need that square root and I need my partials. So I see that z is the square root of x squared plus y squared. We did say above the disk, so we're just dealing with the top half of this cone. Although I suppose we would get the same answer if we were dealing with the bottom half as well, just by the symmetry of it. So this is f of xy. Fx then is x over root x squared plus y squared, and fy very similar. Note that the 2 that comes down from the chain rule cancels the 2 from differentiating the square root. And our square root inside of the integral is fx squared plus fy squared plus 1. And nicely enough, these first 2 terms combine together to make x squared plus y squared over x squared plus y squared is just 1, plus 1 is just square root of 2. So this cone actually turns out pretty nicely. And then our surface area is the double integral of square root of 2 dA. And here we have a circle of radius 2. Its area is going to be pi r squared. It's going to be 4 pi. So we end up with 4 root 2 pi as our surface area. Okay, so then moving on to example 4. So here we want to compute the surface area of the part of this surface that is inside of this cylinder. So let's try to draw out the surface, and then let's make sense of what it means to be inside of the cylinder. Okay, so this surface is z equals x squared minus y squared. Well, if y is 0, if we're in the xz plane, we see we just get something that looks like z equals x squared. So in the xz plane, we have a tracing that looks like this. But if x is 0, then we're in the yz plane, then z is negative y squared. We have something that looks like this. So from y's perspective, we kind of look like a parabola opening down for each choice of x, and from x's perspective, we look like a parabola opening up for each choice of y. Or really what we have here is kind of a saddle point type function. I'm trying to draw this. I know this is a bunch of curves that I'm drawing on here. Might be making it look more jumbled than anything else, but kind of for each downward opening parabola in the y direction, there are a bunch of crosswise upward opening parabolas in the x direction that cross it, and then vice versa. So we have something that looks like a saddle. And we are interested in the area of this surface that's inside the cylinder, x squared plus y squared equals 9. Or this cylinder of radius 3 that would go up and down, but I'm just going to draw the cross section of it in the xy plane. So we see pretty clearly our domain is a circle of radius 3. And then here's our function f of xy. So fx is 2x, fy is negative 2y, and my integrand is going to be root of 4x squared plus 4y squared plus 1. And I'm integrating that over this circle. As kind of a side note, kind of interestingly, the look and the behavior of something like this with a saddle point looks and feels very different from something that's like a paraboloid x squared plus y squared. But we actually kind of see that the surface area is unaffected, right? If this was z equals x squared plus y squared instead, I mean, this minus 2y versus a plus 2y for df dy, the negative just gets squared off either way. So we end up with the same thing either way. So a little bit of just an interesting side note there, that between the paraboloid and this kind of the strange like saddle point kind of thing, it actually has the same surface area over a given region, since it's just really this negative sign that makes a difference, even though many other aspects of the behavior are much different between the two. Okay, so I need to integrate this thing dA. And of course, both the domain of integration and the integrand itself with the 4 times x squared plus y squared are just asking to be put into polar coordinates. And also, I noticed that integrating 4x squared plus 4y squared plus 1 isn't going to be super nice anyway, right? Even integrating 4r squared plus square root of 4r squared plus 1 is not going to be super nice. But again, when we move into polar coordinates, we get the r dr d theta, and that r makes our integration so much easier. So moving over to polar coordinates is going to make this easier in just about every way that it could. So I see theta is going to go from 0 to 2 pi. R is going to go from 0 to 3. And then I have square root of 4 r squared plus 1 times r dr d theta. I note that nothing inside of the theta integral depends on theta, not the bounds of integration on r or the integrand. There's no thetas in there. This is just going to come all the way out and just give me a 2 pi. And then I want to integrate 4r plus 1 to the 1/2. Actually, might need a little more room here. That's going to give me 4r plus 1 to the 3/2 over 3/2 or times 2/3 4r squared. Sorry about that. If I differentiate this, I get 3/2 canceling the 2/3 times 4r squared plus 1 to the 1/2. That checks this off. And then the chain rule pops out an 8r, but I only have 1r, so I need a 1/8 as well. Or I have 4 over 8, so that's 1/2 times pi, so that's pi over 6. Oh, and evaluate it from 0 to 3. So it's pi over 6, 4 squared plus 1 to the 3/2 from 0 to 3. And when r is 3, we get 9 4s are 36, 37 to the 3/2, so 37 times square root of 37. And then when r is 0, we just get 1 to the 3/2, so minus 1. So not the prettiest number in the world, but that's what it is. Okay, and then the last thing we're going to do is look at something a little bit more abstract. So at this point, we might have seen surface area twice, actually. Maybe once in Calc 2, surface area for a two-dimensional surface, right, embedded in 3 dimensions. Once in Calc 2 and once in Calc 3. Now in Calc 2, we only handled the pretty special case of a surface of revolution. But nonetheless, we might have seen a formula for the surface area of a surface of revolution in Calc 2. And anytime that we kind of come up with a new way of approaching a problem, we want to make sure it's consistent with any old ways that we had of approaching either that problem or special cases of that problem. So that's what we're going to check here. So first, we're going to talk about the Calc 2 way of developing the formula for surface area of a surface of revolution. And then we're going to see, is this new way that we developed consistent with that? Okay, so a little bit of a work back to Calc 2 for just a minute here. So suppose I have a function y equals f of x between a and b, and I'm going to rotate this about the x-axis to trace out a surface of revolution. So I have this surface, and I want to find its surface area. So maybe what I could do is take, instead of going all the way from A to B, maybe I could take a small slice of this, say with delta x, and look just at that small slice. Okay, so if I come over here and just pull out this slice, I'm going to exaggerate this just a little bit. So I have something like this. On one side of the slice or the other side of the slice, the radius might be a little bit different. I know that this distance is delta x. And here I'm thinking that I pick delta x small, and that, again, f is a nice continuous function, all those nice things. So if I pick delta x pretty small, then I can do two things. One, I can estimate the along the curve distance, my kind of in the direction of the x-axis distance is delta x. So then the along the curve distance is going to look like square root of 1 plus f prime of x squared delta x, approximately, until we take a limit. The other thing I know if I pick delta x to be small is, so here's my x-axis kind of coming through the middle here. My radius is going to be about f of x. It's going to be about the height of the function for a given input x. So I have something that if I pick a small delta x, this is kind of like a cylinder. It's close to a cylinder. What's the surface area of a cylinder? Well, it's the circumference, 2 pi r, or 2 pi f of x here, times the kind of height of that cylinder. And here, if I kind of cut this out, if I cut this little, say, ribbon of paper and laid it out flat, the height, so to speak, in this direction would be this here, root 1 plus f prime of x squared delta x. So this is the approximation to the little chunk of surface area that we got from this slice. Then we, of course, add them all together and then take a limit. And then that delta x turns into a dx. So for the surface area of a surface of revolution like this is our formula. Now the question is, can we recover this formula from our more general double integral formula? Okay, so let's see, what would this surface of revolution look like in 3 dimensions? So here I'm going from x equals a to x equals b. I have my function y equals f of x. So in the xy plane, that function looks something like this. It comes over to the other side in the xy plane and looks something like this. And then as I rotate it around, it looks something like that. All right, so a couple of things I need to figure out here. I need to figure out a domain of integration, and I need to figure out my z equals f of xy. So for just to make things easy, I'm going to note that this surface area is 4 times the surface area that's in the first octant. So this lets me make z bigger than 0 and y bigger than 0. And that just gets rid of some annoying little details with absolute values and things like that that we might have to be really careful of otherwise, or like plus and minus square root kind of things. And So we're just going to deal with the first octant, and then we're going to multiply by 4 to get the whole surface area. Okay, so well, let's look at our region of integration D first. And I see that's just this region. This is a pretty easy region to understand. X goes between A and B. Y goes between 0 and f of x. Now, what about z equals f of xy? This can be a little tricky. So I'm going to consider a plane perpendicular to the x-axis that is cutting through this surface. I'll call this px. And I see that when I cut through the surface, because this is a surface of revolution, that slice is a circle. What's the radius of this circle? That would be an important thing to know. Well, I know that it might be a little hard to see now, but I know that the distance of this curve away from the x-axis is always going to be f of x. So this circle has radius f of x. Once we pick x for a given choice of x, this is a constant. That's the radius at that point on the x-axis. Now to orient ourselves, going up here, this is the z direction, and going left to right, this is the y direction. So I have a circle that's centered at y equals 0, z equals 0, with radius f of x. This is y squared plus z squared equals f of x squared. Or this is z equals, keep in mind we're in the first octant, so we don't have to deal with all the pluses and minuses and that stuff. So z equals square root of f of x squared minus y squared. This is my quote f of xy, or I'm going to now call it g of xy. We kind of stole f up here. So the thing that is inside the integrand, that's what we're now calling g. So we're calling this surface z equals g of xy. Okay, so I think we are ready to set things up here. So my surface area is what? Well, it's the integral from x equals a to b, just coming back up here. Y equals 0 to f of x. And of course I need to do my integrand next, which is a little bit messy, so I'm going to come over here and do it off to the side. So gx now, my integrand is going to be root gx squared plus gy squared plus 1. Gx, I have to be careful here. I have the square root of some stuff with x's in it, so that's going to give me a 1/2 root of stuff times the derivative of the stuff inside with respect to x. That's going to give me a 2 f of x. And easy to leave off, right? We differentiated now f of x squared with respect to x. So that's 2 f of x to the first times the derivative of f of x times f prime of x. Easy to forget that last little part, that last little link in the chain, but we did get it here. And if we had missed it, we would have seen, how the heck are we going to get this f prime of x coming out of somewhere? But we got it, I think. So GUI a little bit simpler. Just minus y over the square root. And then we have gx squared plus gy squared plus 1. Well, they both have the same denominator. So gx squared is going to give me, oops, that 2 shouldn't be there. My 2 canceled out with the 1 over 2 root stuff. So g squared is going to give me f of x squared, f prime of x squared. Gy squared is going to give me plus y squared. And then plus 1 is going to give me a copy of this denominator. Oops, minus for that. Squared. These y squareds go away. And I see that I can factor an f of x squared out of both terms, leaving me with a 1 plus f prime squared. So square root of gx squared plus gy squared plus 1 is going to be, well, the f of x squared can come out of the radical as just an f of x times root 1 plus f prime of x squared over square root of f of x squared minus y squared. And when I bring this over here, when I put this integrand inside the integral, I note that the entire numerator only depends on x. So it can all come out of the y integral. And then I'm just integrating this and then dx. Now this might look like a terrible integral to do for the y, but it's actually not that bad. Keep in mind that integrating dy, x is held constant. So this f of x squared is just some number, and the f of x at the upper bound here is also just some number. We could do a trig substitution here, or we could just kind of remember or look up that the integral from the integral from u equals 0 to alpha of 1 over root alpha squared minus u squared du, which is exactly what we have here for alpha equals f of x, just some constant, and u equals y. We can do a trig substitution. We can find that this is the arcsine u over alpha from 0 to alpha, or this is just pi over 2. So this entire inside integral here is just pi over 2. And I need my 4 in front. So I see that my whole surface area is 4 times pi over 2, or that's 2 pi. Integral x equals a to b, f of x root 1 plus f prime of x squared dx. And that is the integral that we came up with the other way, the more geometric way, I suppose. So we do see that the two are consistent, that this integral works for the special case, and that we now have a more general version. We have a definition that can handle surfaces that are not just surfaces of revolution. Okay, so that wraps up our discussion of surface area. Uh, so tomorrow in class, we will discuss the next couple of sections, 15.7 and 15.8, triple integrals in cylindrical and spherical coordinates, and then another supplement later this week on changing variables.